Hello and welcome to this video lecture on measuring exposures and health outcomes. In this session we're going to look at measures of occurrence, also called measures of frequency, and measures of association, also called measures of effect. In this session we're going to look at defining and understanding how to calculate a range of measures of exposure or health outcome occurrence, prevalence, and incidence. And we're going to also define and understand how to calculate a range of measures of health outcome or disease association, also called measures of health outcome or disease effect. Risks, rates, odds, risk and odds ratios, and risk and rate differences. Risk and rate differences are not discussed in detail in this session because they are used less often and the principles are the same as for risks and rates. We're going to look at the principles behind how to select these various measures and when to use them, and we'll finish off with applying some of the concepts in this session in the apply session. Remember, epidemiology is about estimating the occurrence or frequency and distribution of health outcomes in populations, and particularly investigating the magnitude of association or effect of exposures on the frequency of health outcomes. So let's look at the key measures of exposure and health outcome occurrence, prevalence, and incidence. Measures of disease occurrence are quantitative calculations, estimations of how common an exposure or health outcome is in a population during a specific period of time or at one point in time. Three numbers are therefore needed: cases, people exposed or with a health outcome; the population, the research study population or the wider target population; and time, the time over which people studied or the cases were identified or the people exposed. Prevalence. Prevalence is a measure of disease frequency of existing cases. It's defined as the proportion of people in a defined population that has the exposure or health outcome at a specific point in time. Prevalence is therefore the number of existing cases at time t divided by the study population at time t. And let's look at an example here. Prevalence of a health outcome would be number of existing adults who have heart disease who live in England in 2020 divided by the adult population 18 plus years, both without heart disease and with heart disease, who live in England in 2020. And looking at the prevalence of exposures, we would have number of existing adults who eat foods with sugar who live in England in 2020 divided by the adult population who both eat foods with sugar and don't eat foods with sugar who live in England in 2020. Prevalence is usually given as a percentage, and percentage and proportion often mean the same thing in everyday use and in epidemiological general use. However, to be accurate, proportion is usually from 0 to 1. And therefore percentages are a special type of proportion that go from 0 to 100%. There are two broad types of prevalence: point prevalence and period prevalence, and generally they are seen as the same thing or very similar thing. So point prevalence occurs at a single point in time. This is from a single research study or information on a specific day, week or month, while a period prevalence is prevalence during a specific time period. And this is usually a year, but sometimes can be months or many years. Now let's look at some examples of prevalence. So point prevalence could be the proportion of the population that has doctor-diagnosed diabetes on the 25th of December 2020 in England, or the percentage of children in London who are obese at the start of primary school reception year on the 1st of October 2021. And a period prevalence would be the percentage of people in a village south of Johannesburg, South Africa, that had malaria parasites in their blood in a survey carried out between October and November 2022. And the proportion of people who are smokers in the year 2023 in the United Kingdom. So how do you find out about prevalence? Well, generally we use existing health information that we're already collecting. And this can be anonymized statistics collected by health organizations, collected at national level, for example, health profiles at borough, district level, at national level, collected from primary care centres, hospitals and other health and social care organisations. Or we can do a descriptive cross-sectional study. And we do a cross-sectional study to investigate either an exposure or a health outcome in a population, but we would not be interested in connecting the exposure to the health outcome. We would just be interested in understanding the prevalence of a disease or a health outcome and the prevalence of an exposure or a health outcome. And an example of an exposure would be obesity or the amount of sugar people were eating, and an example of a health outcome would be number of people with a certain type of cancer, or a number of people who have a cold, or the number of people with HIV. And an example of that would be how many people use safe-sex behaviours, or how many people have an STI in 2021. And you could do that in a cross-sectional study. So how does it work? Let's look at a visual example. So we have a population. We have our participants who are invited to participate in our research, and ideally they're a representative sample of the wider population. And we'll have numbers of people with the exposure, high or moderate levels of sugar in the diet, and the number of participants with no exposure, no or low sugar in their diet. And we would calculate the prevalence of the exposure, the prevalence of people eating high to moderate levels of sugar in their diets. And another way to say that would be the percentage and number of people eating high to moderate levels of sugar in their diets at one point or period in time. And also, of course, the percentage and number of people eating low or no sugar in their diets at one point or period in time. And we could do the same for health outcomes. So we have our population, we have our study participants, and then we have the number of participants with a health outcome such as high or moderate levels of heart disease, and the number of participants without a health outcome with low or no heart disease. And again, we can calculate the prevalence of the health outcome, the prevalence of heart disease. And that would be the percentage and number of people with high to moderate levels of heart disease at one point or period in time, or the percentage and number of people with low or no heart disease at one point or period in time. Now let's move on to incidence. Incidence is a measure of disease frequency of new cases. And the definition is the proportion of people in a defined population that has just been identified as having the exposure or the health outcome at a specific point in time. So that's the difference between prevalence and incidence. Prevalence is about existing numbers of people with exposure or a health outcome, and incidence is about the number of new people with an exposure or a health outcome at a given point in time. So we have incidence as the number of new cases at time t divided by the study population at time t. And an example would be for health outcomes: number of new adults who have been diagnosed with heart disease in 2021 who live in England divided by the adult population 18 plus years, both without heart disease and with heart disease, who live in England in 2021. And we could do the same with incidence of exposure. Number of new adults who started going to the gym who live in England in 2021 divided by the adult population, both those who go to the gym and those who don't go to the gym who live in England in 2021. So let's look at some examples of incidence. The incidence or number of new cases of people living in the UK population that have new doctor-diagnosed diabetes in 2022. The incidence, number of new cases of people with new malaria symptoms in a village south of Johannesburg, South Africa, attending a health clinic between October and November 2020. And the incidence, number of new cases of new chickenpox in children in London in December 2018. So how do we find out about incidence? We can again use existing health information, anonymised statistics collected at local and national levels, e.g. primary care centres, hospitals and other health and social care organisations, as well as local authorities, other health agencies such as cancer registries and national government departments. We can also do a cohort study. We can do a cohort study to investigate an exposure and a health outcome in a population, and because we are following people over time, we can calculate the incidence of the health outcome. So for example, we might do a cohort study on people using unsafe sex behaviours and whether they get HIV in the UK, and from that study, because it's done over time, 5-10 years, we can find out the incidence of HIV in the UK, assuming that we have a representative population who are participating in our study. So why and when to use prevalence and incidence? Prevalence tells us how big an issue is at one moment in time, an exposure or health outcome in a population. It is useful for exposures and health outcomes of interest that are relatively stable, that start slowly and stay for a while. For example, cardiovascular disease or obesity. Incidence tells us how big an issue is growing and becoming. It is useful for health outcomes that start quickly and go away quickly, because either people recover or die, for example Ebola or cholera. And there's two types of incidence that we can look at: risk and rate. Risk is the number of new cases of a health outcome in a population without a health outcome during a defined period of time, in a population that is at risk of the health outcome at the start. This assumes that at the start and end, the population free of the health outcome is exactly the same, i.e. that no one has died from anything, including the health outcome we are interested in. Rates are the number of new cases of a health outcome in a population at risk during a defined time period. This measures how much exposure each person in the population has, and therefore gives a more precise estimate of exposure. So when looking at one group of participants, risks are the number of participants who get the health outcome divided by the number of people exposed at risk at the start. And rate is the number of participants who get the health outcome, exactly the same as for risk, but divided by the person years at risk. Not just the number of people, but the person years at risk. Rates are therefore more accurate when measuring disease occurrence than risk. That's why we identify rates in cohort studies rather than just the risk. The challenge though is that rates are more difficult to understand intuitively. We understand what a risk is more easily than we understand what a rate is, because person years is a very odd concept. Just to look at what is the difference between a risk and a rate with an example. So here we have 7 people in our study, cohort study, and 2 of them have died of the health outcome we are interested in. And these are the 7 people that we are interested in, that we started our study with. And so the risk is 2 people died divided by the 7 people who started in our study, and that's 2 divided by 7, so that gives 0.29 deaths a year. However, if we use a rate, we would actually look and see that not everyone has stayed for the 2 years of our study. Person number 1 stayed for the whole 2 years. Person number 2 died after 1.5 years. Person number 3 died after 1 year. Person number 4 survived and stayed the whole 2 years. Person number 5, we lost them to follow up. They didn't take part in the study after the first year, and we don't know where they went. Same with person 6, they stayed for 1.5 years, but we don't know what's happened to them. And then person 7 moved away from the area and stopped participating, and so they were at risk and involved in the study for 1 year. So therefore the rate is 2 deaths divided by the number of person years, and the calculation there gives 2 divided by 10, which leads to a rate of 0.2 deaths per person year. So you can see here that the rate is giving a more accurate reflection of how deaths are related to exposure. They are more difficult to talk about because we have to talk about the rate of deaths rather than the risk of death. So let's look at an example of incidence risk in more detail. So we have the risk of students dropping out of a course while studying at UWL, and this is for illustrative purposes only, it's not a real example. And so we have 100,000 students at UWL and we have 1,000 dropouts. And so the students initially at risk of dropping out is 100,000 because every student could drop out potentially. And the number of new cases of students dropping out in 2020 is 1,000, and the time period is the 1st of January to the 31st of December 2020. And so the risk is (1,000), the students who dropped out, divided by 100,000, which is the students at risk, and that gives us 1 over 100, which is 0.01, which gives us 1%. Or we can write it as the incidence is 1 new dropout for every 100 enrolled students per year, or 1 per 100 students per year. Usually written as either 10 per 1,000 enrolled students per year or 100 per 10,000 enrolled students per year. So remember, risk is a probability. It's always expressed as a proportion between 0 and 1 unless it's converted into a percentage. And risks are most often used for health outcomes that happen only once or to the first episode of a disease. So for example, the risk of lung cancer in the UK is 1 in 13 for men, 7.7%, and 1 in 17 for women, 5.9%. And other names for risks that you might find in the literature are cumulative incidence, incidence risk, and probability. So let's look at another example of how you might see incidence and risk being talked about. The risk of developing coronary heart disease among men aged 30 to 59 years in the USA in 1995 was 58 per 1,000 men. The 1,000 men are men without heart disease but at potential risk of heart disease. Now, a better way that we can talk about this risk is through different age groups by having subgroups and strata of the population. So it's the risk of developing coronary heart disease in the USA in 1995 was 31 per 1,000 in men aged 30 to 39 years, 66 per 1,000 in men aged 40 to 49 years, and 131 per 1,000 in men aged 50 to 59 years. And you can see the value of giving age groups because you can see that the risk increases as the men get older. And that is a better, more useful guide to the risk than age group from 30 to 59 years. Now let's move on to rates. That's, as we said before, the number of new cases over person time at risk. And you can think of rate and memory aid is with that T. That T is about person time. Rate has a time component in the denominator, as we've said before, but person time, while more difficult to understand intuitively, takes account of changes in the size of the population at risk, and therefore it's very useful when exposures change quickly. It's a sum of the time each person in the study population remained at risk during the study. Hence, rates are usually worked out in cohort studies. Remember, rates are not a probability, it's not a risk, it's different, it's a rate. Rates are most often used to estimate incidence of recurrent illnesses. The rate of severe diarrhea in Ethiopia was 200 episodes per 100 children years. Other names for rates are incidence rate, incidence density, force of morbidity. Now let's look at some examples of rates. Population 1 has a rate of 400 deaths per 1,200 person years, and population 2 has a rate of 600 deaths per 800 person years. Now it's very difficult to compare these two because the person years are very different. So what we do is we create a general denominator, and usually that is a multiple of 10. So for this example, 400 per 1,200 person years converts to 33.33 deaths per 100 person years. That's 400 divided by 1,200 multiplied by 100. And we can do the same with the second rate. 600 per 800 person years is 75 deaths per 100 person years. And that's 600 divided by 800 multiplied by 100. And so you can see that the second group of people with the 600 deaths has a higher rate of deaths than the group with only 400 deaths. Now let's look at a visual diagram showing the difference between risk and rate. So here we have the incidence risk, or the risk over time t, and it's the number of deaths divided by the population at the beginning. So that's the study participants who have the health outcome or have died, divided by the number of people who were invited and who got involved in our study at the beginning. And the rate is the study participants who have the health outcome or who have died over the person years at risk, which is this yellow four-sided shape in the middle. And odds, which we haven't looked at but we will come on to in a moment, odds are the number of people who have the health outcome divided by the number of people who don't have the health outcome. Now, something interesting happens when the risk is very, very small. So when the risk is very, very small, you can see here that the number of people with the health outcome is really small and the study population is large. Then you can see that the person years at risk is very, very similar to n, so that y becomes very, very similar to n. And the same happens with odds. So what happens is that when the risk is very small, both the rate and the odds are very similar to the risk. So we can use them instead of calculating the risk. We can use rate and odds as a proxy measure for risk. And in this example, it's about a rare disease. And so, for example, mesothelioma is a very rare disease, very small numbers. And so here in this context, a cohort study with where we calculated the rate would be very similar to the risk of mesothelioma in the population. So when do we and how do we choose between a risk and rate? So if the health outcome is rare and the population is stable and does not change quickly, so it's a rare disease and a stable population, then the population at risk at the start will be similar to the person years at risk. So it doesn't matter which one we use. And so a rate is actually very helpful. However, there are some additional statistical differences between rates and risk, but we don't need to think about them now in terms of how to calculate confidence intervals. But if a health outcome is common, then we need to choose the most accurate measure, whether that's a risk or a rate. We need to work that out depending on the context of the health outcome that we are studying. And usually the rate will be the more accurate measure of disease occurrence. Now let's move on to odds. Odds is the number of new cases over the number of people who are not cases. So it's not a risk because we're not considering the whole population during the time period. It's not a rate because we're not considering the population at risk again during the time period. So odds are used in case control studies. This is because we choose participants with the health outcome. Purposely, we don't start with the population without the health outcome and then follow them up over time. No, we start and we choose participants with the health outcome and go back in time. Odds can also be used in studies such as randomized control trials and analytical cross-sectional studies, though remember, as said previously, risk ratios are better when there is a choice compared to odds. So where we can use a rate, rates are better and more accurate than a risk, and risks are better and more accurate than odds. So let's look at an example of the difference between a risk and an odd. Let's say we have a lecture theatre and we've got 200 students and we observe them for an hour, and the outcome we're interested in is sneezing at least once, and we find that 50 students sneeze during the 1 hour lecture. So the risk of sneezing is 50 divided by 200, which is 0.25 or 25%. So the risk of sneezing in a 1 hour class with 200 students is 25%. 1 in 4 students are likely to sneeze. But the odds of sneezing are 50 divided by 150, i.e. the number of students who did not sneeze, which is 200 minus 50. And that gives an odds of 0.33 or 33% odds. Now you can see here that the odds is greater than the risk. So odds generally overestimates the actual risk unless the risk is very small. And this links back to when we talked about when risks are small, then rates are very close to what a risk is. And when risks are large, then the rate is likely to be a more accurate measure. In this context, when risks are small, odds and risks are very similar, but when risks are large, the odds will overestimate the actual risk. Hence, in this context, using risk ratios and risks is more accurate than using odds ratios and odds. But sometimes we have no choice, for example, in case control studies. So now let's move on to measures of association or measures of effect or magnitude of effect. And the two key ones are risk ratios and rate ratios. So when we're comparing two groups of participants, and we've already looked at that in a number of previous video lectures, so the risk ratio is the risk in the exposed divided by the risk in the not exposed, and the rate is the rate in the exposed divided by the rate in the not exposed. And so when we look at an example of a measure of association between two groups, we start with the population and invite some study participants who are ideally representative of the wider population. And we have in this context an intervention group, let's say, randomly chosen, and a not exposed group of people randomly chosen. And then we find the number of participants who are exposed in the intervention group who have a change in health outcome. And we find the number of participants who have been exposed in the intervention group but who don't have a change in health outcome. And then we do the same in the control group, find the number of participants in the control group who are not exposed but who do still have a change in the health outcome, and the number of participants who are not exposed in the control group and who don't have a change in health outcome. And that gives us the risk or odds of change in the health outcome in the exposed group, in the intervention group. So that gives us the risk or odds of change in the health outcome in the exposed group of people in the intervention group, and the risk or odds of change in the health outcome in the not exposed group of people in the control group. And then when we divide the risk or odds in the intervention group by the risk or odds in the control group, we can calculate the risk ratio or the odds ratio between the number of participants with a change in health outcome in the exposed intervention group compared with the number of participants with a change in health outcome in the not exposed control group. And these participants, of course, are followed up over time. So let's look at an example. Let's say we have a population. We choose our study participants, and they happen to be a group of men and women with high blood pressure but no other health problems. And so we give that one group of people with high blood pressure a 12-week yoga program, and the control group, we just give them the usual care from their doctor. We want to then find the number of participants being exposed in the yoga intervention group who have normal blood pressure, and the number of participants being exposed in the yoga intervention group but who continue to have high blood pressure, i.e. the yoga group has had no effect. And then in the control group, we want to look at the number of participants who were not exposed to the yoga program and had just usual care, but they also find that they have normal blood pressure, and then the number of participants with no exposure to the yoga program who have continued high blood pressure. And so we can calculate the risk and odds of normal blood pressure in the exposed yoga intervention group, and we can calculate the risk or odds of normal blood pressure in the not exposed usual care control group. And from that we can calculate the risk ratio or the odds ratio between the number of participants with normal blood pressure in the yoga intervention group compared with the number of participants with normal blood pressure in the usual care control group. So let's look at some examples of calculating risks. Here we've got a 4x4 table. So let's look at risk of death in smokers. What do you think the numbers are? You can pause it at this point to try it yourself. we have 50 because there's 50 deaths in smokers, and the total number of smokers was 400, so that gives us 0.125, which is 12.5%. That's the risk of death in smokers. So if we look at the risk of death in non-smokers, that's 10 divided by 600 gives you 0.01667, which is 1.667%. And so the risk ratio is 12.5 divided by 1.667, which is 7.5, or 750%. Now let's look at the same example but calculate the odds ratio. The odds of death in the smokers is going to be, again you can pause this and work it out yourself, 50 divided by the number of smokers who are still alive, which is 350, gives us 0.14286 odds, and the odds of death in non-smokers is 10 divided by 590. That's the number of non-smokers who are still alive, who haven't died, and that gives us an odds of 0.01695 odds. And so the odds ratio of smokers compared to non-smokers, deaths in smokers compared to non-smokers, is 0.14286 divided by 0.01695, which gives an odds of 8.428. Now you can see here that the odds were higher than the previous slide where the risk was 7.5. Let's just have a look at that just to remind you. So if we go back, remember it's 7.5, so you can see here that the odds are higher. The odds overestimate the potential risks. Now remember, odds and risks are not the same thing, but when risks are small, then the odds are very close, very similar to what the risk value will be, but not in this case. So let's look at another example of a case control study. Again, slightly different numbers. Again, let's see if you can do it. So the odds ratio in this context of a case control study is cases divided by the controls. And so in terms of cases, what do we have in terms of odds? Yeah, we have 120 who smoked and 80 who did not smoke, and then the control is 100 who smoked, 300 who didn't smoke, and then that gives us 120 divided by 80, which is 1.5, and 100 divided by 300, which is 0.33, and that gives an odds of 4.5. And so if you have lung cancer in this context, this table example, you have 4.5 times the odds of having smoked. And you can turn that around and say, so that if you smoke, you have 4.5 times the odds of getting lung cancer. This does not mean you're 4.5 times more likely or more at risk of getting lung cancer. Remember, odds overestimate the risk. And the reason we can't calculate risk in case controls, as I've mentioned previously, is because we are starting out with people who already have the disease, the health outcome, and then we're going backwards in time. But there are some other advantages as well, because probabilities, risks are between 0 and 1, and odds that can be between 0 and infinity. So there are some statistical advantages to odds compared to risk. So how do we look at working out whether something is significant, something might be a causal association? And the things we use is confidence intervals and p-values. We use statistics to work out whether a result is because of random error, chance, or is a true finding. And we do that by thinking about the null hypothesis and whether that is true, which is that there is not a true finding, it's just happened by chance, or whether the null hypothesis is false and that we do have a true finding. So Epidemiology is odd in that we start with a hypothesis that says there is no difference between the two groups we are looking at. There is no difference between the intervention group or the control group. There is no difference between the people who are exposed and who are not exposed. That's how we start off with. And we try and prove that that is as true, and when we find that that is not true, that there is no difference true, then we can say that there is a real difference between the two groups. It's a bit counterintuitive. Instead of saying the hypothesis is that there is a true finding, we say the hypothesis is that there is no true finding, that the result we've got is because of chance. And that's important because most of our findings will be like that. And so the way we work out whether the null hypothesis is true or not is by using confidence intervals and probability values. CEIs and p-values assess the role of chance. However, they don't tell us anything about bias or confounding. Yes, they only tell us about the role of chance. So if we do have bias or confounding in our study, then that is a different problem and is not solved by confidence intervals and probability values. So when a confidence interval or p-value shows that the finding is likely to be true, we say the findings are statistically significant. So significant is not important, it just means that it's significant as in there is likely to be a true difference between the two groups, that this is a true finding, that the null hypothesis is false. So let's look at what confidence intervals are. Now, remember, if we think about a research project, it's unlikely that the exact finding we get in a research project is true for the wider population. It's much more likely that we've got a finding that's useful and relevant to the people that took part in our study, but is not accurate for the wider target population. For example, the risk ratio, rate ratio, odds ratio in the study participants is not likely to be exactly the same as in the wider population. So the confidence interval gives us the range of values within which we think the true value for the wider population lies. So for two or more groups being compared by dividing the measure, the risk ratio and odds ratio, the confidence interval range should be above or below 1 for statistical significance. Remember, when we're dividing things, when the number at the top is the same as the number at the bottom, the answer is 1. So when there's no difference between two groups in a risk ratio or an odds ratio, then risk ratio or odds ratio will be 1. And so to find a real difference, we would have to find a confidence interval that gives a range that is above 1, that does not include 1, or is below 1, again does not include 1. If it does include 1, then there is a potential that the true result, the true finding in the wider target population is that there is no difference between the people who are exposed and the people who are not exposed. So if it encompasses 1, then there is likely to be no difference between the exposed and the unexposed participants in our study. So there would also be no difference between the exposed and unexposed in the wider target population. For one group being studied, risks and rates for example, or two groups being compared by subtracting one from the other, a risk or rate difference, then the confidence interval range should be above or below 0. Remember, if you're comparing one group, then 0 would be 0 risk or a 0 rate. And if we're subtracting one thing from another, 0 would mean the two numbers are exactly the same and we get a subtraction of 0. So this is the difference, and it can be confusing. So when we're talking about risk ratios and odds ratios, the confidence interval should be above or below 1 to show statistical significance. But when it's a risk or a rate or a mean or a difference, then it has to be above or below 0 to be statistically significant. Confidence intervals are more useful than p-values. They're more useful because they give more information on the true finding in the wider target population. P-values only tell us whether a finding is statistically significant, i.e. there is a real difference, or not. But it does not tell us anything about what the true value in the wider target population is likely to be. Confidence interval does allow us to do that. So let's look at an example of a confidence interval for ratios. Let's look at an example that is not statistically significant. A confidence interval of 0.5 to 1.5 is not statistically significant, and this is because it includes 1. And a visual representation of this would be, imagine an exposed group and their confidence interval, and an unexposed group and their confidence interval, and what you'd find is that the exposed group confidence interval overlaps with the unexposed group's confidence interval, so that the target population true finding, for example deaths in the wider target population if people are exposed, could cut across the confidence intervals for both the exposed group and the unexposed groups, meaning that the deaths, for example, could be the same across both groups. So i.e. there is no real difference. So what we want is confidence intervals should not overlap. And for a statistically significant finding, therefore, a confidence interval would be above 1, 1.2 to 1.4, or below 1, 0.2 to 0.9. And visually this would look like this, where the confidence intervals for the exposed group and for the unexposed group do not overlap. So therefore, even at the lowest level of the confidence interval for the exposed group, the findings, for example deaths, would continue to be higher than they would be for the unexposed group. There is no overlap. So there is no way that the true finding could be one that would be the same for the exposed group and the unexposed group. A p-value indicates the level of significance associated with a particular conclusion or study finding. The closer the value is to 0 or 0, the more likely it is that the intervention is responsible for the effect, i.e. the null hypothesis is false and that there is a true relationship between the exposure and the outcome. For example, comparing yoga to no intervention in 65-year-old women, we might find that participants receiving the yoga perform better in terms of mental health and well-being than those receiving no intervention, with a p-value of 0.05. So this would mean that the yoga affected mental health and well-being, and that this difference between the two groups was not due to chance. It was a true finding. The null hypothesis was false. There is a real difference between the two groups. So the p-value tells us the probability of obtaining a finding, a risk, a rate, a risk ratio, a rate ratio, or an odds ratio as high or higher than the value found in the study, assuming that the null hypothesis of no association is true. So when the probability is low, 0.05 or less, then it's likely that the null hypothesis is false, i.e. there is a true relationship between the exposure and the outcome. Another way of saying this is that it gives a degree of belief in the null hypothesis. Is the null hypothesis true, or is the null hypothesis false? And remember, you have to look at the exact value. Don't just go for generalized values or just people saying statistically significant. Look at the actual p-value. And in this context, confidence intervals are better than p-values. Usually a p-value equal to or less than 0.05 is seen as statistically significant, and this means that the likelihood of the result we got in our study is due to chance is 5 in 100 or 5%, which is a very small chance. And this value is typically used in public health and social science research, and most public health interventions in the research that we look at will be measured at this level. But there is no reason why this level is chosen. It's just a consensus view. And in medical research, often testing new drugs, the p-value can be equal to or less than 0.01 or 1% chance. And the reason for that is that we want that drug to work very well, and we want to be very cautious because of the negative impact side effects of drugs. So we want the result to be highly likely not to be due to chance. Now that's a quick overview of measures of occurrence and measures of association, as well as confidence intervals and p-values. We will do some examples in the practical, and you can also look at this website, which also gives more statistics around cancer that uses incidence and prevalence to just enhance your understanding of this topic. And please also look at the reading list and the materials on Blackboard, which will again enhance your knowledge and understanding about measures of occurrence and measures of association. I hope you found this video lecture useful. Look forward to seeing you in class. Take care. Bye bye.